Okay, welcome back, students. Let's continue on with section 5.3. Okay, 5.3 is on the Gram-Schmidt process. Okay, and this process is to find orthogonal basis. Okay, theorem. Okay. The Gram-Schmidt process. Okay, let x1, x2 to x of m be a linearly independent set of vectors in an inner product space V. Okay. Then an orthogonal basis. So this just takes my independent set of vectors and it turns it into not only a basis, but an orthogonal basis. That's kind of cool. Okay, it doesn't turn it into an orthonormal one, but it does turn it into orthogonal. Okay. So vectors and let be linearly independent set of vectors in a product space. And then an orthogonal basis for the subspace of V spanned by these vectors is, it's really a basis, an orthogonal basis, okay, is the subspace. So we're creating an orthogonal basis out of the subspace whose vectors are v1, v2 to v sub m. Okay, where v1, we start with just taking x sub 1, the first vector in the subspace, in the space. Okay. And then v2 is going to be equal to x2 minus the inner product of x2 v1, which is x1. But you'll see in a second why I don't put x1, I just put v1. Okay, over the norm of v1 squared times v1. Okay, so that kind of creates a v2, okay, based on x1, x2, and v1. And then V3 is equal to X3 minus, okay, X3 with inner product with V1 over V1 squared V1. So that's very similar to the second term of V2, but then we end up with a third term where we're taking the inner product of X3 with X2 because we have two variables, two values that we can work with, X3, okay, and I should say V2 from the previous one, all over the magnitude of V2 squared. Oops, that should be on the, it shouldn't be magnitude, I'm sorry, it's norm. The norm of V2 squared with V2 times V2, okay? Okay, and then this just continues for however many vectors I have in the in V, okay, in the vector space V. Okay, and this just equals x of m minus the summation of k equals 1 to m minus 1, okay, of xm inner product with vk, just to kind of generalize this process, over vk squared times vk itself. Okay, so we do this process for however many vectors there are in the vector space V. Okay, so let's try this out. Okay, so number one, obtain an orthogonal basis for the subspace of R4 spanned by 1, 0, 1, 0. Okay, 1, 1, 1, 1. Okay, and negative 1, 2, 0, 1. Okay, now keep in mind this is not a base. It's going to be a basis for the vector space. It's just going to be a basis for the subspace spanned by these vectors. Okay, because there's only 3 vectors here and we're in R4. In order for it to span all of R4, you'd need 4 vectors. Okay, so the number of vectors would have to equal the dimension. Okay, and so this is just the subspace spanned by these vectors. Okay. Okay, so what's V1? V1 is equal to X1, which is, this is X1, this is X2, and this is X3. Okay, so V1 is equal to X1, which is just 1, 0, 1, 0. Okay, so the first one is easy. It's just the first one. Then it gets a little bit more complicated because we have V2 is equal to X2 minus X2 inner product space with V1 over the magnitude of V1 squared. I keep saying magnitude, it's the norm, sorry. Norm of V1. I'm keep switching between physics and math, and so it's hard with the terminology. But I'll get it. Okay, V1. Okay, and so that's X2 or V2. Okay, so let's work on our product, okay, for these vectors, which is just the dot product in R4, okay, the standard inner product, okay, in R4. So x2v1 is going to equal 1, whoops, yeah, x2v1 is going to be equal to x2, which is 1, 1, 1, 1. Okay, with x1, which is 1, 0, 1, 0. Okay, which is just going to be equal to 1 plus 0 plus 1 plus 0. Oops. 1 plus 0, which is 2. Okay. Okay, if I did, okay, so the 2 is going to be on the top. Okay, now let's find out what's the norm of v1 squared. So the norm of v1, okay, squared, that's going to be equal to the square root for the norm, but then I'm going to square it, so those are going to cancel each other out. And it's really just going to be v1 standard inner product with v1. Okay. Okay, and so this is just going to end up being 1, 0, 1, 0, dotted with 1, 0, 1, 0, which is just going to end up being 1 plus 0 plus 1 plus 0, which is again 2. Okay, so let's kind of put this together. V2 is equal to x2, which is 1, 1, 1, 1, minus the inner product of x2 over x2 v1, which is 2, over the norm of v1 squared, which is just 2, times v1, which is just 1, 0, 1, 0. Okay, and so this just goes to 1. If I subtract, I get 1 minus 1, which is 0. Okay, and then 1 minus 0, which is 1. And then 1 minus 1, which is 0, and 1 minus 0, which is 1. And so that's V2. Okay, so I was able to get V1. Let me highlight this. Okay, I was able to get V1 as that guy. Okay, and now we're able to get V2 as that guy. Now we're going to use V1 and V2 to get V3. So you can tell that this becomes more and more complicated as we go on. Okay, which is why I really didn't want to do one that spanned all of R4, because that would be 4 iterations of this, and it just gets really big, really fast. Okay, very complicated, very fast. But let's do one more. V3, what's V3 going to be equal to? Okay, V3 is going to be equal to X3 minus X3 inner product with V1 over the norm of V1 squared, V1 minus X3 V2 all over V2 squared V2. Okay, so let's find what's X3 dotted with V1. Okay, standard inner product for x3 v1. Okay. Okay, is going to be x3 v1, x3 with v1. Okay, so that's going to be negative 1, 2, 0, 1. Okay, dotted with 1, 0, 1, 0. Okay, and it looks like only one of these terms is going to survive. Negative 1, 2, 0, 1 is x3. Okay, and that's going to be negative 1. Okay, so this is negative 1. That's the only term. The first term is the only one that survives when I dot those together. Okay, let's find out. We already know what v1 squared is. We used that in the last one. That was 2. Okay, and we know what v1 is, so that's good. Let's find the inner product for x3 and v2. So the inner product for x3 v2, that guy, negative 1, 2, 0, 1, and then what was v2? It was the opposite of this. It was 0, 1, 0, 1. Okay, so like here, 2 and 1, the 2 survives, and the second term, 2 times 1, plus the last term, which is the last component, I guess I should say, is 1 times 1, which is 2 plus 1, which is 3. Okay. Now all I have to do is figure out, well, what's the norm of v2? Okay. Well, and squared, right? So the norm of v2 squared is just 2, because if we look at the norm of v1, we just had 1, 0, 1, 0. So when we square all those, that's 1 squared plus 1 squared, 1 squared plus 0 squared plus 1 squared plus 0 squared, that just becomes 2. And then square root that to get the norm. And here we have 0 for v2, we have 0, 1, 0, 1, and has basically the same component, just in different order, but it's still going to be 1 squared. So we'll say the norm of v2, it's going to be 1 squared plus 1 squared, which is 2. Okay, is equal to the square root of the squared of v2, which is equal to 0, 1, 0, 1, dotted with 1, 0, 0, 1, 0, 1, which again, that's just going to be squared and square root, cancel out, and that just becomes 2 again. Okay, so what would v3 be? v3 would be okay, x3, which is my negative 1, 2, 0, 1, okay, minus x3 v1, which we said was negative 1, over v1 squared, which was 2 from the previous one. Okay, that was up here, boom, 2. Okay, and then times v1, which was 1, 0, 1, 0. Okay, minus, this is going to be 3 is the next numerator, and then the denominator is going to be v squared over 2, but that's the same thing as, that's right here. Okay, v2 squared, that's 2, and then that's going to be times v2, which v2 we found to be 0, 1, 0, 1. Okay, so now let's just distribute and combine these. These negatives are going to cancel to become positives. Okay, and so we get negative 1, 2, 0, 1 plus distribute the 1/2, 1/2, 0, 1/2, and 0, and then distribute the negative 3/2. This is 0, negative 3/2, 0, and negative 3/2. Okay. So now we get negative 1 and 1/2 is negative 1/2 plus 0. It's negative 1/2. 2 plus 0 minus 3/2, that's negative 1/2. Okay. And then the next one, is it negative 1/2 or positive 1/2? Let me think. Be sure. Oh, no. Oh, because we have 2, right? So we have 2 plus 0, right? 2 plus 0 plus negative 3/2. Okay, that's going to be positive 1/2. Positive 1/2. Okay, 0 plus 1/2 plus 0, that's just a positive 1/2. Okay, and then 1 plus 0 plus negative 3/2 is negative 1/2. So there's V3. And this will create V1, V2, V3. Okay, we'll create an orthogonal basis. So what is that orthogonal basis? Well, V1 was 1, 0, 1, 0. Okay, V2 is 0, 1, 0, 1. And V3 is negative 1/2, 1/2, 1/2, and negative 1/2. And so that is an orthogonal basis. And we can see that this is orthogonal. If we were to actually dot product any pair of these, if I did one with V1 with V2, okay, the standard inner product, I would find that I get all zeros. That's fine. Okay, and then V1 with V3, I would get negative 1/2 plus 1/2, which goes to 0. And then if I did V2, I would get the same thing. V2 with V3, I would get negative, or I would get positive 1/2 plus negative 1/2, that goes to 0. So they're all orthogonal. And it is an orthogonal basis for the subspace. Okay, for the subspace spanned by 1, 0, 1, 0, 1, 1, 1, 1, and negative 1, 2, 0, 1. Okay, so this is an orthogonal basis for the subspace spanned by those vectors. Okay, so basically what we did was we took non-orthogonal vectors and turned them into orthogonal vectors. Okay, so that's kind of cool. Okay, let's try another one of these, but instead of using the standard inner product, we're going to use the function inner product, where we have to do some integration. Okay, to determine an orthogonal basis for the subspace of P naught from -1 to 1 spanned by the functions f1 equals x, f2 equals x cubed, and f3 equals x to the fifth. So we want to find an orthogonal basis that will span these guys. Okay, so the first thing we know is that v1 is equal to x. Okay. The second thing is v2 is equal to, okay, f1, sorry, f2, I should say, f2, because that's, I'm going to call it, you know, this, it would be like it would be x2, but I don't want to use x's because x is the other variable, so I'm going to use f, okay, as my vector that we're working with. Okay, working with x cubed, you know, our polynomials, our functions that we're working with. So f2 minus the inner product space of f2 v1 over the magnitude of v1 squared. Okay, so let's see what these are. So the f2 v1, okay, is going to be equal to the integral -1 to 1 of f2, what's f2 x cubed, times v1, what's v1? It's x, okay, dx, which is equal to -1 to 1 of x to the fourth dx, which is equal to x to the fifth over 1 from -1 to 1. Okay, so this is going to become 1, sorry, over 5. I put 1 there, 5. And so this becomes 1/5 minus -1/5 because of the odd power, which becomes 2/5. So that's just 2/5. Okay, what about the magnitude of v1 squared? Well, this is going to be the square root squared, so those are going to undo each other, and then it's just v1, okay, with the function inner product being, you know, on v1 squared basically. So this is -1, 1 times x, which is x squared dx. Okay, so this is going to be equal to x squared integrated is x cubed over 3, okay, which is going to be, oh, and this is times f1. There we go. Is it f1 or v1? It's v1, I'm sorry. v1, which is the same thing. Okay, so x cubed over 3 from -1 to 1. This is going to do the same thing. 1/3 minus -1/3 is equal to 2/3. Okay. Now we can figure out what v2 is. v2 is going to be equal to f2, which is x cubed, minus the inner product of f2 v1, which is 2/5, over the norm of v1 squared, which is 2/3. Okay. Times v1, but v1 is just x. So this becomes the x cubed minus 3/5 x. Okay, and that's v2. We found v1. V1 is x. Is this guy here. Okay, now let's go on to figure out what V3 is. Okay. So V3 is equal to F3 minus F2, or sorry, F3 V1 over V1 norm squared times V1 minus F3 V2 over V2 norm squared. Okay, V2. Okay, so what's F3 with V1? Okay, F3 with V1, that's going to be the integral from -1 to 1 of x to the 5th times x, which is just x to the 6th. Which is x to the 7th over 7 from -1 to 1. And because, again, it's odd, this is just going to become 1/7 minus -1/7, which is 2/7. Okay. Okay. Okay, so what is F3 V2? Okay, so F3 V2, this is going to be -1 to 1 of x to the 5th times times V2, which we calculated to be x cubed minus 3/5 x dx. So that's going to be equal to -1 to 1 x to the 8th minus 3/5 x to the 6th, okay, which is going to be equal to x to the 9th over 9 minus 3/5 times 1 over 7th x to the 7th, evaluated from -1 to 1. Okay. If I plug in 1, I get 1/9 minus 3 over 35. Minus, if I plug in -1, I get -1/9 plus 3 over 35. Okay, which is going to give me, if I distribute the negative, that's going to give me 2/9 minus 6 over 35. And if I subtract those with a common denominator, I get 16 over 315. Right? Some fun numbers to work with. Okay, and then what's V2? V2 squared, well, that's just going to be the inner product of V2 with V2. Okay, which is going to be -1 to 1 of x cubed minus 3/5 x times itself. Right, so that dx is going to be equal to -1 to 1 of x to the 6th minus 6/5 x to the 4th, okay, plus 9/25 x squared dx. Okay, so this is going to be equal to -1 to 1 of, oh, let's do the integration, sorry. It's going to be x to the 7th over 7 minus 6 over 25 x to the 5th plus This is 3. So this is 9 over 75. X to the third, which can be reduced to 3 over 25. And evaluate from -1 to 1. So this is going to become 1/7 minus 6/25 plus 3/25. Okay, minus -1/7 minus actually at the plus 6/25 minus 3/25. Right? So if we distribute the negative sign and combine, this becomes 1/7 minus 3/25, and this becomes plus 1/7 minus 3/25. Okay, and so this becomes 2/7 minus 6/25. And I get, these are relatively prime, 7 and 25, so you could just multiply like that, and you would get 50 minus 42 over 175, which is going to be 8 over 175. Okay, so another fun number to work with. Okay, so what's the goal here? The goal is we're still trying to find V3. We had to find all these, difficult constants. Okay, so what is V3? Let's rewrite V3. Okay, V3 is equal to, okay, VF3 minus F3V1 over V1 squared, norm of V1 squared times V1 minus F3V2 over V2 squared V2. Okay. So F3 is just x to the fifth. Okay. F3V1 we found to be 2/7. That's minus 2/7 over the magnitude of V1, which we had already calculated to be 2/3. Okay, and then V1, which was x, right? Okay, minus, okay, f of 3V2, that was the 16 over 315. And that might reduce, I don't know. I mean, I don't think so, unless 315 is divided by 4 or 8. Okay, all over V2 squared, which is 8 over 175. Okay, times V2. And what was V2? It was that x cubed minus 3/5 x. Okay, so let's clean this up. This is going to become x to the 5th minus 2's are going to cancel. The 3 is going to flip up top. 3/7 x minus, this is going to become 16 over 315 times 175 over 8. That becomes 2. Okay, 175 and 315 are both divisible by 5. So 175 divided by 5 is 35. 2 times 35, and 315 divided by 5 is 63. Okay. So we get 15 over 315. Let me do this in the calculator. Divided by 8 over 175. Okay. So yes, okay, so 35 contains 7, and so does 63. So this is just going to become, I can divide the top by 7, that's 5, and the bottom by 7, that's 9, and that becomes 10 ninths. Okay. So 10 ninths. Okay, so minus that all becomes 10 ninths times x cubed minus 3/5 x. Okay. So this is going to become x to the 5th minus 3/7 x minus 10 ninths times x cubed minus 3/5 x. Okay. This I can divide by what's 175 divided by 5? It's 35. So this is 35. Nope. This is just 5. Okay, because I can divide top by 35 and then 315 divided by 35 is 9. So that's 9. Okay, so that's where my 10 ninths comes from. Okay. And then distribute and just combine like terms. Okay, and so this becomes x to the 5th minus 3/7 x minus 10 ninths x cubed minus or plus 30. I'm just going to go 10 ninths times 3/5 because a bunch of things is going to cross cancel. That's 3, that's 2, that just becomes 2. Yeah. Okay, and then that's x, so that's just 2/3 x. And so this is going to be x to the 5th minus 10 ninths x cubed minus 3/7 x plus 2/3 x. What I really need to do is subtract 2/3 minus 3/7, and again, they're relatively prime, so this just can be multiplied by 3, but 3 and 3, that's minus 9/21. This is 7 and 7, so that's plus 14/21. Okay, and so my final result is V3 is equal to x to the 5th minus 10 ninths x cubed plus 5 over 21st x. Okay, so that's a V3. Okay, so let's put this all together and say that an orthogonal basis, okay, an orthogonal basis of x to the 5th, x to the 3rd, x is V1, which is just x, V2, which was that x cubed minus 3/5 x, and then V3, which is x to the 5th minus 10 ninths x cubed plus 5/21 x. Under the standard inner product, or not the function inner product. That's their answer. Okay, fun with fractions, right? Yay, yay. Okay, and that's it for 5.3, the Gram-Schmidt process. And I'll see you in the next section, the next chapter.